This class I am going to discuss about characteristic of infinite capacity multiple solver Poisson cube model. We can say it is model 2 also. So characteristic of infinite capacity multi-solver multiple solvers Poisson cube model. We can say model 2. Symbolically we can represent it as MMS, where solver is not one. In the previous model, we had single solver, infinite capacity, but here we are using multiple solver and infinite capacity, and the Q discipline is FIFO. So in this case, there will be no change in the arrival rate, but there will be some change in the service rate. So what happened? In this model, there are S servers working independently. If there will be less than S customer, only N server will be busy and the others are idle. Others are idle. Hence, in suppose number of customer is more than the number of server, there will be waiting. If the number of customer is less than the number of server, there will be no waiting. And so we will have two possibility for the service rate. Whereas there is no change in the arrival rate. So what we will do here? Here we take we take lambda n as lambda, but we have mu n, two values. What are those values? We will consider n mu if 0 is less than or equal to n is less than s. The number of customer is less than number of server. And the second one is s mu if the number of customers are more than the number of servers. So these are the two cases we will consider for the service. Okay, and hence we can have two values, corresponding values of p0 and pn. So we have pn in the previous model. Pn is nothing but lambda to the power n divided by mu1 mu 2 mu and so on, so n mu into p0. Lambda mu1 mu2 mu3 means here n equal to 1 means mu1, n equal to 2 means mu2, n equal to 3 means mu3. So mu1 will be 1 mu, mu2 will be 2 mu, mu3 will be 3 mu, and so on. And so finally what we will get? 1 into 2 into 3 up to n is n factorial. So we will get 1 by n factorial into lambda by mu to the power n into p0 into p0. And this is the case when the number of customers are less than the number of servers. So this is the value of pn. Similarly, when the number of customers are more than the number of servers, so what will happen there? In that case, we will have, for n is greater than or equal to s, we have pn equal to lambda will be unchanged, so lambda to the power n, and in the thing we will have up to 1 mu 2 mu and so on, so s minus 1 mu into, thereafter we will have s mu into s mu and so on. So how many times? It will be nothing but n minus s plus 1 times into p0 into p0 into p0. And so if we rewrite this one again, what will get? 1 2 3 up to s minus 1 is 1 by s minus 1 factorial. 1 by s minus 1 factorial. Now you see mu s minus 1 time. So I will have mu to the power s minus 1. Mu to the power s minus 1. And then here I will have s mu up to n minus s plus 1 times. So that means I will have 1 by s mu to the power n minus s plus 1 into p0 into p0. If we simplify it, we will get this one as we'll get this one as 1 by s factorial into s to the power n minus s into lambda by mu to the power n into p0. And this is the case for n is greater than or equal to s. So we are having two values of n when n is less than s and n is greater than or equal to s. So we can write both the values of Pn like this. Pn will be nothing but 1 by n factorial lambda by mu to the power n into p0 if 0 is less than or equal to n is less than s. And second value is 1 by s factorial s to the power n minus s into lambda by mu to the power n into p0 if n is greater than or equal to s. So these are two values of Pn. What about P0 then? So P0 will also have two values and we will calculate them and we will finally write Pn. Okay. So similarly, in order to calculate P0, we will write like this. We have summation Pn n equal to 0 to infinity is 1. But this n equal to 0 to infinity has two parts. One is up to s, other one is beyond s. S minus 1 and s to infinity. So I can write this one as summation n equal to 0 to s minus 1 and we can have one pn here plus summation n equal to s to infinity. I will have another pn and that is equal to 1. So this Pn is for n is less than s and this Pn is for n is greater than s. So if you put them and if you simplify them, so this is equivalent to saying summation n equal to 0 to s minus 1 and that time Pn will be nothing but 1 by n factorial 1 by n factorial lambda by mu to the power n and then summation n equal to s to infinity. This Pn is nothing but 1 by s factorial 1 by s factorial s to the power n minus 1 lambda by mu to the power n and common is p0 that is equal to 1. That is equal to 1. So if you put all the values and we will simplify it, finally we will get p0 will be nothing but 1 divided by summation n equal to 0 to s minus 1 1 by n factorial lambda by mu to the power n plus plus 1 by s factorial into 1 minus lambda by mu s into lambda by mu to the power s. So this will be our value of P0. Once after calculating P0, we can able to calculate Pn and Pn P1, P2, P3 and so on. So we can able to calculate. Okay. So this is the procedure to find the Pn. Here we can put the value of P0 depending upon the nature of server, means how many servers are there, then we can able to get the value of Pn. So here also I want to discuss some characteristics. So first characteristic is average number of customer in the queue. Average number of customers in the queue. Average number of customer in the queue, that we always denote as LQ. And so E of LQ is equal to E of NQ, and E of NQ is equivalent to E of N minus S. Number of customers in the queue. Average number of customer in the queues is the number of customers who are more than number of servers. And so this will be equivalent to summation n equal to s to infinity n minus s into p n into Pn. So if you substitute the value of that and if you simplify, we will get LQ equal to 1 divided by, we can get it in this form, LQ equal to LQ equal to 1 by s factorial into s into lambda by mu to the power s plus 1 all divided by 1 minus lambda by mu s to the power 2 into p0 into p0. So this is the average number of customer in the queue in case of model 2. In case of model 2. And next characteristic is average number of customer in the system. Average number of customers in the system will be E of ns, that is equal to E of nq, average number of customer in the queue, plus the average number of customer arriving and departing. So that will be nothing but 1 by s into s factorial lambda by mu to the power s plus 1 to the power s plus 1 divided by 1 minus lambda by mu s whole square into p0 plus lambda by mu. Lambda by mu. This is the average number of customer in the system as for model 2, multi-server model. Then the another characteristic of multi-server model is Average time a customer has to spend in the system. Average time a customer has to spend in the system. In the system will be nothing but E of Ws, and that is nothing but 1 by lambda E of Ns. E of Ns, and that is equal to 1 by mu. E of Ns we have already got 1 by mu plus 1 by mu into 1 by s into s factorial into lambda by mu to the power s divided by 1 minus lambda by mu s square into P0. This is the average number of customer waiting or has to spend time in the system. The next characteristic is average number probability that an arrival has to wait. Probability that an arrival has to wait. Probability that an arrival has to wait. That means probability Ws is greater than 0, and it is equivalent to probability n is greater than or equal to s, and that means summation n equal to s to infinity pn. So if you put the value of that and if you simplify it, we will get probability Ws greater than 0. Probability the arrival has to wait will be nothing but lambda by mu to the power s divided by s factorial into 1 minus lambda by mu s into p0 into p0. So this is the probability that a customer has to wait or a arrival has to wait. And the next characteristic is probability that an arrival enters the service without waiting. Probability that an arrival enters the service without waiting. That is nothing but 1 minus probability an arrival has to wait. Because probability of waiting in the queue plus probability of getting service will be equal to 1, and so this will be the thing. So this will give you 1 minus lambda by mu to the power s divided by s factorial 1 minus lambda by mu s into P0. This is the characteristic that a probability of an arrival enters the service without waiting. And then next characteristic is mean waiting time. Mean waiting time in the queue. in the queue for those who actually wait. For those who actually wait. So that will be nothing but E of WQ given WS greater than 0. And so that will be nothing but E of WQ divided by probability of WS is greater than 0. And if you put all the value and simplify, you will get 1 by mu s minus lambda, the mean waiting time in the queue for those who actually wait. And the next characteristic is probability that there will be someone waiting. Probability that there will be someone waiting, and that means probability the number of customers are more than s plus 1. There are s servers and customers. If there will be waiting, somebody is waiting, then definitely the number of customers are more than the number of servers, and this will be nothing but summation n equal to s plus 1 to infinity pn. Okay, and it is equivalent to saying summation n equal to 0 to infinity pn minus probability n equal to s. Probability n equal to s. So this will give you the final answer is lambda by mu to the power s divided by s factorial into p0 into lambda by mu s divided by 1 minus lambda by mu. 1 minus lambda by mu. So this is the probability that there will be someone waiting. And the next characteristic is average number of customers who have to actually wait. Average number of customers who has to actually wait. Who has to actually wait will be nothing but L of W. So this is equivalent to E of NQ provided NQ number of customer in the queue are more than 1. And so this is equivalent to E of NQ divided by probability of N is greater than or equal to S. Here S. Okay. And so that is equal to, this is equal to lambda by mu S divided by 1 minus lambda by mu S. This is your average number of customers who has to actually wait. Who has to actually wait. And the final characteristic of this one is probability that a customer has to wait more than time t. Probability that a customer has to wait has to wait more than t time. More than t time. That is p of w is greater than t. P of w is greater than t. And that will be nothing but E of minus mu t whole into 1 plus lambda by mu to the power s into 1 minus e to the power minus mu t into s minus 1 minus lambda by mu all divided by s factorial into 1 minus lambda by mu s into s minus 1 minus lambda by. So this is the probability that a customer has to wait more than time